All right, everybody, where we left off was this little screen right over here. And one moment, please. Oh my goodness, back one, please. There it is. So where we left off, guys, it was with Jill. Jill was doing a whole bunch of work here. She pushed with 200 newtons of force over 10 meters, resulting in the work that she had to put in was 2,000 joules of work. But the thing is, it seems almost like what a sucker would do, because if it only weighs 500 newtons and you're only going up to the truck 2 meters, you could just lift with 500 newtons over 2 meters and you're there. That's only 1,000 joules of work. By using the ramp, she actually did twice as much work than what you would think you'd have to. Who does that besides Jill? Turns out a lot of people, because a lot of people can't lift a big, cumbersome 500 Newton box like this up 2 meters over their head. That's over 6 feet tall, guys, 2 meters. That's not an easy thing for anybody to do. So some of you, sure, you can lift 500 Newtons, but a big box like that up over your head and put it in the truck, that's not that easy of a thing to do. Pushing it with 200 newtons, less than half the force, over 10 meters, pushing it this way, not as cumbersome. So it turns out it took more work by pushing it this way than what she got out of it. Because what she got out of it was 1,000 joules of potential energy, because that's the work done moving straight up. So the next question is, well, we found the efficiency of this. So what she got out was 1,000 joules, which is the weight times the height. What she put in was 2,000 joules. So she only got half of the energy out. That's why it means it's 50% efficient. That means 50% of the work she did is still left over in this box in the form of potential energy, the ability to do something. Well, so that lends another question. Well, where's the missing 1,000 joules? Because if these joules were money, so if I had $1,000 and I put something somewhere and I said $1,000, I'm good with that. But if I spent $2,000 on something that's only $1,000, I'm going, whoa, wait a minute. Why am I blowing 1,000 joules? Why would you do that? Well, in this case, because I probably couldn't get up over my head to get it in the truck to begin with. But it turns out that missing 1,000 joules is somewhere. It has to be. It's called the law of conservation of energy. We don't just create it, we don't destroy it, it's always there. So if she did 2,000 joules of work in, but only has 1,000 joules to show for it, where's that missing 1,000 joules? Where's half the work that she did? Well, guys, do one of these things and push really hard. That's warmth. That feels pretty good. Because what happens when I'm doing work, shoving my hands against each other over a distance, I'm doing some work. And I have something to show for it, guys. Warm hands. But here's my question. How do we get my warm hands to do work? My cold hands do the same work as my warm hands. My warm hands don't do any extra work. So it seems like I've wasted some of my energy. Well, it depends, because it feels pretty good when I do this. But my question is, so I'm doing work to do this. My hands are hot. How can I use my hot hands to do work that my cold hands can't? It doesn't. So when you take that package over there and you rub it against the ramp like that, well, what happens is the ramp is a little bit warmer. Not only is the ramp a little bit warmer, so is the box by 1,000 joules. That's where the energy is. It's called thermal energy. So when you do work, in reality, you create some thermal energy. And in this case, quite a bit, 1,000 joules of it. The plank is warmer, the box is warmer, so the energy is still there, but how do you use it to do work? You can't. So the law of conservation of energy sounds wonderful, guys. The energy is always there, always going to be there. But is it usable? That's the key. Because right now she put 2,000 joules of work in and only half of it's usable as a stored potential energy up there, gravitational potential energy. The other half is still there. It's a nice warm plank in the box by 1,000 joules. But how do you get that to do any work on something? So there's the problem. So today, guys, what you're going to do, you're going to do a little experiment with finding the efficiency of a ramp. But what I want to know is this thing gets steeper? The ramp gets steeper and steeper and steeper. Does it get more efficient, less efficient, or stay the same efficiency? That's the question. So does it mean, so remember, if you're 50% efficient, you lost half your work. If you get close to 100% efficiency, you're not losing much energy. You still have most of it. If you only have 5% efficiency, you've lost 95% of your energy to that thermal stuff of rubbing between your box and your ramp there. So what I want to know is, it gets steeper, are they going to be more efficient or less efficient? That's what you're going to do in today's lab. All righty. So we'll pop that out of there. And let's go right to oh, I forgot to unshare that. No, stop that. Oh, I don't have to stop sharing, because I think you might be able to see this. And in case I'm wrong, I don't want to do this all for nothing. I'm going to do another share. And there it is. Make sure you can see what's going on there. All righty, guys. So you're going to this site right from your student view. There's going to be a Phet thing link to click on. Now, it's an older version. When you click on this, it could take some time because it's a Java thing. They have some special stuff to make that Java work on newfangled internet. Oh, here we go, guys. It's initializing. There it is, guys. It's starting up. Are you getting excited? Are you getting ramped up for this? Phet's made in Boulder, Colorado, if you recognize those mountains over there. University of Colorado. I think they might be out partying. It's Friday night here because, oh, here we go. Now they're starting up. Maybe they're back from the party. Hey, apply a force to that filing cabinet. That means you use your mouse and you push it one way or the other. Look, there's a normal force and there's some weight. And they mentioned something about a friction on this file cabinet. And look, there's a coefficient of friction there. Piano, that's got some friction. Refrigerator, a crate. You can move your dog, maybe. You can make it frictionless. No. If you make it frictionless, you're going to be 100% efficient. And there really aren't any frictionless labs. Okay. In real life, virtually, yeah. But yeah, we're not going to go there. So we're pushing this around. I'm going to start at the bottom, guys. So I got to first click on that, and the dude's going to push it down to the bottom. So here's some things you can do. There is a little position thing I found at the, okay, I didn't say stop, did I? I must have said stop. Go clear down to the bottom. I guess you don't have to start the bottom, guys. So why, what am I thinking? Maybe start at the 5. Okay, so here's a 15. So 1, 2, 3, 4, 5. Oh, that's not equal increments. I'm going to go back to the bottom, guys. All right. I'm going to go back to the 0 position. Okay, whoops, that's not quite 0. Well, close enough. I'm close enough to 0, guys. So my length looks like it's going to be 15 meters. We'll see if it gets to the top, and I may not have to do any trig at 10 degrees, 2.6 meters high to figure out what's going on. There is something to stop, so I can't ramp it off the top of there. But to be as efficient as possible, I don't want to ramp it up really fast. It's going to hit this brick wall and stop. That's going to be some heat energy doing that. I don't want, that's going to lose a loss in energy that it's not getting my file cabinet up there. So to be as efficient as I can, I want to move it up at a constant speed if possible. Okay, so here's what I'm going to do. I'm going to clear my graph down there. I don't know what's going on down there. You sure? Yeah, I'd like to clear that. It's a mess down there. So I need to find the work input and the work output. Now the output work is pretty simple. I'm not, let me do my, okay. Let's go with some pink. So on the work output side of things, let me just do that up here. What I get out of the thing, if I go clear to the top, it's gonna be my force times my distance. And my force straight up is the weight of that thing. It's 100 kilograms. So that's 980 newtons, okay? So 980 newtons, that's my 100 times 9.8. This is Earth, okay? Virtual Earth, it's Earth. 980 newtons. Now the distance it gets moved is 2.6 meters. There it is. All righty. So if I want to find out how much work that is, all I do is 980 times 2.6. Only have a couple sig figs there. 2548. Okay. So it's 2,000. I'm going to go to 3 sig figs, even though technically I can't have that many. 550 joules of energy out. That means that's the potential energy of that thing up there. Is that exciting? Okay, work input now. So it's work out over what I put in. Okay, so my force that my dude is putting in, my distance in is going to be 15 meters, it looks like. I think I'm going to get it to the top. We'll see. I need to get a force. To get a force, I'm going to look at my thingy down here. Here we are, guys. Oh, let me stop my writing. Or maybe I don't have to stop. Can I just push it with my pen? I cannot push it with my pen. But I'm going to try to push it not that way, but up the ramp that direction. All right. So let me stop my annotation. Oh, there it is. I stopped it. Okay. So there it is, guys. I'm pushing that thing up there. All right. Not pushing hard enough. I got it going. But here's the thing. I don't want to accelerate. Oh, no, it's harder because I'm going up a ramp. Got to grunt a little harder. There we go. I'm still pulling it up with my thing. Okay, now I'm really going up fast. I don't want to go up fast. I want to go up as efficiently as possible. Okay. Let me try pushing again. Applied force getting stronger. I'm pulling it even further. There we go. Okay. Uh-oh, I'm accelerating. Okay. Almost 15 up there, and it took about 500 newtons to do that. So let's say it took 500 newtons. Okay. So if it took 500 newtons, that's the area where I was pushing. I was pushing harder and harder. It's what to get it moving. And I stopped. Then I got it static, just a static friction here. And this is where I finally was moving it up with a constant force of about 500 newtons, it looks like right over there. Let me start annotating that again. So I got 500 newtons right over there. So it's a 500 newtons. And I know I didn't quite get to the tippy top. I'm going to pretend I did. Times 15. So that is 10. And so 15 times 5, that's 75, right? And 2 zeros. So that's 7,500 Newton meters or joules. That's the input stuff. That's the dude shoving in the direction of the ramp there. Remember, force and displacement have to be in the same direction. So my efficiency for my run here, my first run of 3, is what I got out to what I put in. It's 2550 to 7500 joules. So divided by 7500, 34%. So I got a 0.34. Okay, so that's a ratio. If I want to make it a percent efficient, it's times 100, which is the same thing as 34% efficient. Okay, 30.34 out of 1. So, wow, guys, I'm missing 2/3 of the work. What happened to 2/3 of the work, guys? Well, remember that little friction thing? 2/3 of the work would have gone into warming up this thing a little bit of over here and the file cabinet. So now what happens when you go higher? So all you have to do is change your angle, and you change your angle right over here. Right over here, you can change your angle and do the same thing over a couple more times and see what happens to the efficiency as you get higher and higher and higher. Use the same thing. You can use the refrigerator, you can use the piano, use the crate, use the sleepy dog for all I care. But use the same item over and over and over and find the amount of work it takes that you put in using the ramp versus what you get out. Remember, when you're going to get more work out because it's higher. Still the same length of plank, but that very well may change the force it takes to push it up. That's what you guys are going to find out. That's what you do in your lab. Okay, so there's a lab sheet there for you to fill out and answer some questions. Have a wonderful day, and I'll see you on Wednesday. Lucky you guys get to see me twice this week. All right, have a good one. Seriously, have a good one.